And finally, the question of inclusion. In my country, we are very aware of the importance of all kinds of inclusivity, including the inclusion of social class. We have a lot of learners in the UK who can't learn because they are simply deprived. But I think there's another kind of inclusion that I'm going to mention in a minute, which is, I'm going to call it epistemological inclusion, inclusion into knowledge. There are people for whom certain kinds of knowledge have been closed. In my own subject, which as you know is mathematics, we allow our students to give up learning mathematics at the age of 16, which is just about the time when mathematics begins to get slightly interesting in school. And so it's like spending 12 years learning to play your scales on the piano, and just as you can possibly begin to play a piece of music, you throw the piano in the dustbin. And we really can do better than that now, thanks to technology. So I'm going to give you some examples. Let me just say a little bit more about what these words mean. Personalization means exploiting not just digital technologies, but I think the adaptivity of digital technologies. We're beginning to see, and it's taken until now, we're beginning to see those people working on adaptivity, making computers responsive to those people, to those learners that are using them. We're beginning to see that happen now, and it's taken a long time. If you think that computers have been around in education now for around 30 years, it's taken until now when you could honestly say we have got examples of computers learning something about what their users are doing. But I challenge you to think of more than 2 or 3 examples that you personally know where that kind of adaptivity is actually being exploited. I have never been in a classroom in the UK where adaptivity has really been in operation, where the computer is actually learning something about the students. I have been in some other countries. So I think we're at the very beginning of that. And I'm going to say more about that as time goes on. So let me give you a couple of examples on this theme of personalization. And the first is one of my own projects that I briefly, very briefly, talked about in the workshop yesterday, although I was very pushed for time, not to mention jet lag. And this is to try to build an intelligent system to share the secret of school mathematics with all those students who never get the secret. And the secret is, we're not really interested in solving problems at all. Because if we give you a problem to solve about real things, that's not the real problem. There's a secret piece of information which is, we want you to generalize. So if you see a pattern of numbers, we ask you what's the next number, and we ask you what's the 10th number. We might ask you what's the 100th number, but we don't really care what the answer is. What we really want you to do is generalize. And we've built a little piece of software which is based on something that our national curriculum in the UK is absolutely full of, which is these spatial diagrams, and asking people, for example, if you have, look on the left of the screen, if you have 5 red squares in this configuration, how many green squares will there be? You see, I haven't let you into the secret. You think that you could find the answer just by counting, right? Of course you could, and that's what students do. And then when you say, okay, how many are there if there are 500 red squares, they say, well, you have to give me, I'll come back tomorrow and tell you. That's a lot of counting. But you don't really care. 500 is just a trick. And the secret is, we want to know how many green squares there are if there are n red squares, or whatever you want to call it. And the truth is, and I say this is one of the few educational research findings that I know I can be confident about, the truth is that a huge number of students drop out of algebra because they never get this trick. It's not that they can't perform the procedures. In fact, thousands, maybe millions of students get full marks in tests of algebra without understanding what it's about. And I think that's a disempowerment. It's a failure of inclusion, because it's a very powerful idea. So the learner constructs something here, and over here something more general happens. The computer shows what would happen in a general case. I'm not going to give you a lesson on this piece of software, but there are things moving dynamically. The numbers of tiles are changing continually. The kinds of ways in which the numbers can be manipulated are dynamic. And all you need to take away with you, obviously you can look on the web for more examples, I'll give you the URL more generally at the end. But all you need to take away from you with this example is two things. One is, if you change the technology with which an idea is expressed, you can find new ways to represent difficult ideas. The difficulty of algebra isn't so much the big idea of generalization, it's the way it's expressed with x's and y's. And when you interview kids, if you're a maths education researcher, and you say, where was it that you dropped out of maths? What was it you couldn't understand? And they say, I couldn't understand those x's and y's. Everywhere around the world, even in Hong Kong, this is probably true, but I don't know. It's certainly true in the United States and the United Kingdom and most of Europe. Now, the other thing is that the system then has to try to understand what it is that the student understands. And this is what I was talking about before. Because it's fantastically difficult. You don't know how many of these squares the student's going to focus on. And if you look at the top left-hand diagram, how do you see that? Do you see that as a red square with 3, 6, 7, 8 green squares around it? Well, you could see it like that, but then you notice there's an overlap with the next square. So there are other ways to think about it. And the computer doesn't know which way the student is thinking about it. The only possibility for the computer is to try to take what the student is doing and make an inference about it. And I went to a very nice workshop this morning about Knowledge Forum that Professor Law's group was giving. And they're tackling the same problem. It's the same problem all around the world, to try to interpret from rather sparse sources of information what the student is really thinking. These sources can be enhanced by tracking eye, for example, which I don't think you are doing, but some people are doing. But this has its own problems. And compared to this amazing computer, which is called the human brain, where we every day make an inference thousands of times per day on what the people we're speaking to are making of what we're saying. I'm doing it now to you, by the way. Trying to infer whether you're asleep or whether your lunch was too good. But you know, to get a computer to understand what the person using it is understanding is very, very difficult. I won't say any more about that. But I think that it gives us an insight into what Professor Seymour Papert calls the graphocentric curriculum. Here's the big idea, and it's his, not mine. The big challenge for us, one of the big challenges for us, is to understand the extent to which our curriculum was devised and based on what happens to be possible to learn with pencil and paper. Grapho means writing, the written curriculum, writing with a pen. That's before writing changed its meaning, which now means using a keyboard, I guess. I don't know what writing means anymore. But that's how our curriculum was devised. It had to be possible for the people we were trying to educate to make some progress just with a pen and paper. And now it's time to look at that curriculum and say, that is not a constraint anymore. We have really quite radically new technologies that make it possible to express similar ideas, or maybe new ideas, in completely new ways.